Thank you. Thank you for the introduction. At the beginning, I want to say thank to the organizers of this conference for ISyDMA’9. It's a great pleasure to be here with you today and to share with you some recent results about Cerium gadolinium doped composites. During the preparation of presentation, I decided to focus exactly on the Cerium gadolinium composite and the possible application of this material in the energy sources. Nowadays, the demand of energy increases every day. It's obvious, and while people want to move away from the traditional sources, they start to use wind, solar, and thermal energy as sources to dissociate the water. After the dissociation, we receive hydrogen and oxygen. This hydrogen we can store, transport, and use in different devices, and use as a source for producing electrical energy in the solid oxide fuel cells. With oxygen from the water, they are sources to produce electrical energy, and with this they complete hydrogen circle. They close it. So if we compare this hydrogen circle, which is part of the green energy, it is known that green energy is environmentally friendly, renewable, and possess high efficiency, while the traditional fossil oil fuels are limited and non-renewable. Therefore, the efforts of the scientists, and therefore in the scientists, is to try to find new devices and new materials for application to produce energy. One among these devices, fuel cells, play an important role. We can divide different types of fuel cells depending on the type of the materials and cycle of operation. And one of them are solid oxide fuel cells, which have high efficiency. They have flexibility in fuel. They can use different type of fuel, low emission, and high stability. Depending on the operation temperature, the solid oxide fuel cells can be classified as high temperature solid oxide fuel cells. These are the fuel cells that operate at temperatures higher than 800 degrees, and low temperature solid oxide fuel cells which operate up to 400 degrees. As you see, the fuel cell market increases with every year, and it is expected to increase further, almost exponentially. Between these high temperature and low temperature solid oxide fuel cells are intermediate solid oxide fuel cells. This type of fuel cells are still on a scientific scale, on scientific level, and a lot of efforts are done and are doing to find materials and conditions that in which these intermediate solid oxide fuel cells will operate optimal. So these intermediate solid oxide fuel cells have some advantages: lower temperature, which of course a reduced cost of the materials, and stabilize the device, and therefore they need to have a lot of properties which make them suitable for application, for this application. Among a lot of materials which are studied nowadays in respect to find best material for intermediate solid oxide fuel cells, rare earth doped cerium materials are one of the studied a lot in the from scientific community. What we know about cerium oxide? It's possess fluoride cubic crystal structure. It's important that cerium is in stable 4+ valency, but it's easy can be switched to the 3+, so it makes a redox couple cerium 3, cerium 4. If we introduce, for example, rare earth or some dopant in this crystal structure, we expect this crystal structure to be deformed, to destroyed or deformed. So we decided to find how it changes this structure of the cerium oxide if we doped with gadolinium, and to find this amount of the gadolinium which we can introduce without changing the structure, without changing the fluoride structure, which is good for application that we expect to study. Therefore, we started with the synthesis of our materials. We applied several methods. First one, high temperature, the easiest method. We found that the reaction is incomplete, and we stopped with this method. So further we used Zoll gel and hydrothermal methods of synthesis. Here is the scheme of synthesis of gadolinium doped with cerium oxide doped with gadolinium using ionic gelation. Two steps. At the beginning, starting with cerium nitride and gadolinium nitride with potassium alginate, and using ionic exchange reactions, we obtain gel, and after that, after drying and thermal treatment, we obtain powder at 500 degrees centigrade. This powder, after we sintered in form of the pellet at higher temperature, higher than 1000 degrees centigrade. Hydrothermal synthesis, we started from nitrides, again cerium nitride and gadolinium nitride, and use potassium base to alkalize the solution. This solution we placed in the reactor, hydrothermal reactor, and using this process at relatively high temperature and pressure, we obtain a powder after washing and thermal treatment at 500 degrees centigrade. And again, the last step was to sinter tablet at high temperature, 100 and 400 degrees centigrade. We started with hard characterization of the obtained samples. The sample obtained by ionic gelation at 500 degrees centigrade show peaks that are broad due to the presence of gadolinium, which is with ion radius higher than the dose of cerium. After the calcination, the peaks become sharper and like this at the hydrothermal synthesis, which is an evidence that high crystallinity we obtain in these samples. From the experimental data of the HIXRD study, we calculated cell parameters, crystal system, and space group. As you see, the space group, the crystal system remains stable cubic, and the cell parameter increases almost regularly with gadolinium content due to the higher size of the gadolinium ion. To study the structure of this material, we use several methods. First one is the infrared spectroscopy. And what we found for the samples obtained at 500 degrees centigrade and from hydrothermal synthesis is that again, except the peaks of the cerium with oxygen and gadolinium with oxygen, we found peaks that belong to the hydrogen and hydrogen with oxygen that comes from water, and also some peaks of carbon and oxygen. Maybe they are come from the air, or probably from some tracks of potassium carbonate, which is the product of the ionic gelation reaction. Next study about the structure, what we performed is the study with X-ray photon spectroscopy. Here are presented the graphs of cerium. They are typical to cerium, with 6 main peaks that belong to cerium 3D, and these 6 peaks are due to the presence of cerium 3+ and cerium 4+. In order to calculate and to see the amount and the amount of cerium 3+, we make an deconvolution of the spectrum and found that a small amount of cerium 3+ we obtain, which slowly increases as gadolinium increases in amount. We studied also peaks of oxygen, XPS peaks of the oxygen. Typical, they are 2 peaks. One of this peak at the lower energy belongs to the lattice oxygen. This is the oxygen that inside of the crystal cell, and this peak belongs to the presence of bonds between metal and oxygen. The other peak that is at higher binding energy visible, it belongs to non-lattice oxygen, defect oxygen, which is due to the presence of defects in some oxygen that is movable in the cell. So it's obvious that with increase of gadolinium amount, the percent and the part of this defect oxygen increases due to the presence of new defects and vacancies in structure after gadolinium introducing. We studied surface of the samples by scanning electron microscopy. And what we found is that samples obtained by ionic gelation has loose structure with relatively big pores, while the samples produced by hydrothermal synthesis have more dense structure, and pores are smaller. The morphology of the samples we studied by transmission electron microscopy, and on the pictures we see very clearly the difference between the shape and the form of the samples. Well, first, what we can say is that the samples obtained by ionic gelation tend to agglomerate, while the hydrothermal synthesis, the samples are visible separately. So, in the form of the shape of these particles is different, almost circle in the ionic gelation, and in the hydrothermal synthesis they are square. The interesting thing here is that with increasing gadolinium content, we obtain some nanorods. And these nanorods, the number of these nanorods increases as gadolinium increase. We think that this is due to the synthesis, to the condition of the synthesis, and if we change the temperature, for example, or the pressure and the time, maybe we will see a different shape as we've found in the literature. From the data obtained from electron dispersive X-ray spectroscopy and elemental mapping, we saw that they are homogeneous and the composition is close to the initial. At the end of our study, we performed some electrical measurements. Here are shown the results from these measurements which we performed using impedance spectroscopy. The data for real part of the electrical permittivity are shown on these figures, and we found that the values decrease by orders of magnitude when gadolinium is the amount of gadolinium is increased. Obviously, the values decrease also with the frequency of the investigation. From the experimental data, from this data, we calculated the conductivity of the materials, and the results show that with 10% gadolinium in the samples, we found orders of magnitude higher conductivity at temperature 700 and 650, 700 degrees centigrade. It is interesting that with 30% gadolinium, we found that the conductivity, the values of conductivity decreased. Yes, I'm close to that. Okay. So, what are our conclusion after all this investigation? The ideal cell of the cerium oxide, which we see on the left side, is deformed and not destroyed but deformed after introducing gadolinium, and this is a cubic form still, but deformed along the volume diagonal due to the presence of gadolinium, which facilitate and induce vacancies and defects that make these changes in the structure. And then here I summarize our results. So if we introduce gadolinium, you do not change the structure of the cerium, which is good for our purposes, and different types of materials we find in the shape and in the size. And what we find that these materials looks that they are suitable for energy application, but of course a lot of work is still in progress, and we expect to receive new results soon. So, thank you for your attention.